Welcome to the Week 7 workshop. This video will introduce the questions here. The first question involves estimating the mass of the Earth's atmosphere. Just a ninja physics estimation. Now there are kind of two ways to do it. One way would be to think of the volume of the atmosphere and multiply by a density to get the total mass. A lot of people try to do this by using volume of a sphere, the radius of the Earth, 6,400 kilometers, and then a bigger sphere, 6,400 plus the thickness of the atmosphere, and taking the difference between the two. And that's fine, but it's kind of overkill, because you have to bear in mind the atmosphere is actually very thin. Here's my highly sophisticated prop. If this was the Earth, the atmosphere is like the thickness of a piece of paper on the surface. So actually it's a very good approximation to say the total volume of the atmosphere is just the surface area of the entire Earth multiplied by the thickness of the atmosphere. The next question is a very famous ninja physics question, the Julius Caesar's last breath. Now, somewhere a little over 2,000 years ago, Julius Caesar, the Roman general, was assassinated. And presumably before he was assassinated, he was murdered, he was breathing. And so sometime before everyone stabbed him, he had a last outward breath. Now that breath went out into the atmosphere of the Forum in Rome, and in the 2,000 years since then has spread pretty thoroughly around the world. The question is any of that last breath in each breath you take now? If I take a breath now, are there any atoms in there that were also in Julius Caesar's last breath? Now you need to estimate the volume of a breath. Let me do a demonstration. Here's the bag. I'm going to take a breath. So, there you go, that's the volume of a breath. I mean, you could argue about whether Julius Caesar's last breath would have been a little bit more, smaller than normal, stabbed, or whether he's only got half a breath through, but yeah, ninja physics, don't worry about that. The more tricky bit is working out the number of atoms. Now, you can do this using moles, especially if you've got chemistry training. I personally find that all very confusing. I find an easier way is just to use the atomic mass and the atomic mass unit. So, for example, oxygen has an atomic mass of 16, which means it's got 8 neutrons and 8 protons. Neutrons and protons have about the same mass for ninja physics purposes. And the mass of a neutron or a proton is called the atomic mass unit, which is 1.66 by 10 to the minus 27 kilograms. So you can basically say it's got an atomic mass of 16, so 16 times the atomic mass unit, 1.67 by 10 to the minus 27, gives you the mass of one oxygen atom. Oxygen's diatomic in the atmosphere, so you have to multiply by 2 to get an oxygen molecule. And so if you can use that to work out the mass of one molecule, you've got the total mass of all the air in your bag, the ratio of the two tells you how many atoms are in there. Now for the rest of the workshop, we're going to be doing some modelling of global warming. And before we get started on that, I'd like to talk a little bit about the physics of global warming, which is probably unfamiliar to most people. You've probably all heard the stories about CO2 traps the heat like a blanket, makes you hotter, but it's a little bit more to it than that. Now, this is really a lot about the interaction of radiation with matter. Now, electromagnetic radiation is basically oscillating electric and magnetic fields. So electric field oscillating up and down, points up, then it points down, then it points up, then it points down, and you get a magnetic field that's going at right angles. Now what's relevant here is actually mostly the electric field. And let's imagine you have a charged particle, say an electron. It's got a negative charge. So when you have an electric field pointing up, it's going to push the electron down, and vice versa. So whenever radiation comes past a particle, it will cause that particle to move, to oscillate, to vibrate. And that's the fundamental thing we're going to talk about here. So now let's look at how an oscillating electric field, which I will show with this blue arrow in the simulation, affects a molecule, not a single charged atom. So here we've got CO2, with the carbon in the middle and the oxygen at both sides. And because of the details of the chemical bonding, these are not all electrically neutral, there is some charge distribution. So when you apply electric field, it'll pull the ends up and the middle down, or vice versa. Now let's run the simulation for a very slowly oscillating electric field and see what happens. So the electric field is oscillating and it's pulling them up and down, but doesn't have very much net effect. It causes it to vibrate a little, but there's no obvious pattern. Now that's true if the frequency of the electromagnetic wave, the frequency of the oscillation of the electric field, is slow. Now let's make it a bit faster. Okay, so now we're going to oscillate a bit faster and see what happens. And now we're seeing a much more violent motion, a sort of vertical motion. It's called the bending moment. What's happened here is that the oscillation of the electric field has hit a resonant frequency. It's a frequency that this atom or molecule would like to vibrate at naturally, and so it's causing a very large bending moment oscillation. Now if we increase the frequency of the electromagnetic radiation a bit further, so it's an even higher frequency of oscillation, we're now no longer in the resonance, so it's not having the big effect. It's going too fast. But if we make it faster still, we're now seeing a linear motion with the oxygen going in the opposite way so the carbon going in the opposite way to the oxygen, but now all in a straight line rather than a bending. So in this case there are two resonances. And if you make it even faster still, not much effect. So what happens is when you get molecules like this, they have a series of different resonances for different sorts of vibration, bending and linear, and if you hit them with radiation at that resonant frequency, it'll cause very strong oscillation, and if you hit it with some other frequency, it won't. And that turns out to be absolutely crucial for global warming. Now this is a rather busy diagram, but let's have a look at it. So what we're plotting here is wavelength in micrometers. And we're starting down here at 0.2 micrometers, which is ultraviolet. Then we go up to about half a micrometer, which is visible, and then also to different sorts of infrared. This region here is more or less called near infrared, and this one around here is middle infrared, and there's far infrared, which is off to the right and not shown on this graph. Now, at the top diagram, we're looking at how much light, the spectral intensity of the light, and the red diagram is the light coming in from the sun, which is more or less a black body with a temperature of 5,500 to 6,000 Kelvin. So the red line is the energy coming in from the sun. That's the radiation heating up the Earth. The Earth is surrounded by a very large amount of vacuum, so we're not getting any conduction and convection to or from the Earth. It's all radiation. Now the heat going out, it depends on how hot the Earth's surface is. So they've got three different lines here for three different temperatures of the Earth's surface, for the very coldest bits of Antarctica up to the hottest bits of the deserts. But all of it's by and large in the mid-infrared out at around 10 microns, whereas the visible light's around half a micron. So this is the radiation coming in, this is the radiation going out. There are different wavelengths. Now if the atmosphere was transparent to all wavelengths, or there was no atmosphere, then all of this would come in and all of that would go out and the two would balance. But in practice, the atmosphere is very far from being transparent. This is a diagram showing what fraction of the radiation gets through the atmosphere as a function of wavelength. Now you can see that down here in the visible, the atmosphere on a clear day or night is actually fairly transparent. Most of the radiation gets through. Down here in the ultraviolet, very little gets through. That's because of the ozone layer. But then when you get into the infrared, you'll see that there are some wavelengths where the light gets through and some where it doesn't, and another one where it does, another one where it doesn't, another one where it does. So it becomes almost like a sawtooth pattern where there are certain wavelengths get through and certain don't. As an astronomer who often does infrared work with telescopes, I am deeply familiar with this pattern because we have to design our telescopes to work in these atmospheric windows, as we call them. For example, this window is called the J, this is called the H, and this is the K band. And I spent an awful lot of my life studying distant galaxies with instruments tuned to work in the K band. Whereas if I tried to tune it to work over here, I wouldn't be able to see anything unless I had a space telescope because the atmosphere is opaque. So what's causing this pattern? Well, here are the different components. The main one is water vapour. So water vapour causes absorption, no absorption, absorption, no absorption, absorption, no absorption, a whole series of wavelengths, and it is by far the major thing blocking infrared light. Why does water do this? Well, let's increase our simulation with water. So H2O, big O in the middle, 2H on the outside. But the major difference of water is that the molecules are not all in a line, and that means they can do a lot more stuff. They can do all the vibrations that carbon dioxide does, but because they can also rotate, they can do a lot more. They've got rotation about 3 axes, they've got all sorts of funny patterns. And as you can see, lots of stuff goes on when you start accelerating. Each bond can stretch and bend and twist, and the whole thing can rotate. It's like some sort of mad boxer going crazy. So that's why water vapor causes such a range of absorption, such different waves. Each of these corresponds to a different type of vibration or rotation or combination of vibration and rotation. So water vapor is the main global warming factor. It's a natural one, it's always been the case. Even in the 19th century, scientists had worked out that if you were to strip away the water vapor from the Earth for even one night, you'd awake to everything frozen solid. This is actually why the diurnal range, the temperature from day to night in Canberra, is so great, because it's very dry here and we're relatively high altitude, about 600 meters up. When you get a clear, dry night, there's not so much water vapor, so a lot of the infrared radiation can escape, so the temperature can plummet. So even though it may be in a hot day, the temperature drops a lot at night. Whereas if you're in somewhere like Sydney or particularly Brisbane or Singapore, where it's much more humid and low altitude, there's always a lot more of this water vapor absorption, so the heat can't escape so much at night. But that's not what's causing global warming. Global warming, because water vapor is relatively constant. We're not putting more of that out by polluting the Earth. We are putting out huge amounts of carbon dioxide, and in particular it has these 3 bands, which are due to 3 different types of vibration. And it turns out that one that actually dominates global warming is this band over here, which is due to the bending out of alignment vibration. That's because these 2 bands, they also absorb, this one also overlaps with water, so the radiation can't get out anyway. This one doesn't overlap with water, but the Earth isn't really cool enough to emit very much there, whereas this band's right near the peak of where the Earth emits. So this, the bending moment vibration, is what's responsible for global warming. So you see, when electromagnetic radiation hits CO2, depending on the frequency, it can cause 3 sort of dance moves. There's this type of vibration. That's what I call the Egyptian dance. And then there's the up and down dance. And it turns out it's this latter one that causes global warming and has toppled numerous governments around the world.